Hi everyone, this is still Mr. Soko, and this is the processing of our uh, virtual experiment on the different atomic models. Okay, so I hope you've done the experiment well, and then you get to have some insights on how the atomic concept developed. Okay, so this is just a very short discussion, so we trace from the very start, okay, from a philosophical idea to a scientific theory, the development of the atomic model. Okay, so there was this one man in Greece, okay, credited for asking the question, what do you get if you continuously cut a piece of gold until you reach the point when you can cut it anymore? Okay, so this is some sort of a legend or a story that has been handed down through so many generations. Now, it has been pointed out that it was Democritus who has started speculating about things. Okay, and then he asked that question. Okay, and he called those particles, those indivisible particles, atomos. Okay, which are primarily uncuttable particles, which retains the property of the object. So, as early as the ancient Greek civilization, the people were already thinking about their natural world and they're trying to explain them. Okay, and what such notion is the springing forth of the idea of indivisible particles called atomos. Okay, which has also been the basis of the word atoms. Okay, so which are the building blocks of matter? Okay, that's the layman's term, building blocks of matter capable of participating in chemical reactions. Now, right now, we very much know, or we know very well, that there are other subatomic particles or other particles comprising an atom. So it may not be basic anymore. Okay, now after 2000 years, the story was Democritus' idea stood up against Aristotle. So Aristotle thought that there are four elements that make up matter. Those four elements are air, water, earth, and fire. So the idea of atomos was mm, shunned away by people. They believed more in Aristotle. Okay, so it was only after 2000 years that the idea of the atom has re-emerged through the person of John Dalton. Okay, so but before that, we need to talk about first the development of a theory and a model. So a theory is a set of unifying principles which are well validated hypotheses that are used to explain. The key word there is explain. It's a collection of um, body scientific facts and understandings that are used to explain a phenomenon. While a model, just like what we are having now, is a representation, it is a mental construct, okay, or how we visualize things. A representation of things which may be very difficult to perceive. Okay, so according to John Dalton, all matter is composed of very small particles called atoms. Okay, and all atoms of a given element are identical. Okay, and atoms cannot be created nor destroyed or subdivided in any physical or chemical change. So this is where his theory got wrong already. But he is right when he said they can be rearranged to form new substances, which we will learn later on. Okay? Or more technically correct term is relearn later on. In chemical reactions, atoms combine with or separate from other atoms, and in chemical reactions, atoms combine with each other in simple whole number ratios to form combined atoms. For example, two hydrogens and one oxygen atom make up water, H2O. Two oxygen atoms and one carbon atom make up carbon dioxide, that's CO2. So simple whole number ratios. Okay. So he called his model the billiard ball model, as what you have previously experienced in the virtual lab. So that is his billiard ball model or the solid sphere model. So next came the discovery of the subatomic particles. Now one very important subatomic particle that was discovered is the electron. Okay, the electron is a negatively charged subatomic particle, and then it was through Joseph John Thomson or J.J. Thomson, okay, that the notion of the electron was discovered. And how did he do it? Well, he just used the cathode ray tube experiment, okay, which paved way to the discovery of charged subatomic particles in an atom, particularly the electron. Okay, so this is what how the experiment looks like. So you have here a negatively charged end, which we call the cathode, and a positively charged end, which we call an anode. Okay, now what happens here is there is a cathode ray that is bombarded from one end to another, and a phosphorescent background strip so that the ray will be clearer. Now there is also a slit there where the bombarded rays come or pass through. So what happened now? Once they turn on the ray, okay, there is kind of a radiation or a luminescent light that happened, okay, traveling from the negative end to the positive end. And they noticed that if there is an interacting magnetic field, then there is a deflection of that ray. Okay, and it so happened that that interaction paved way to the idea that there must be something in the atom that interacts with current, or that is responsible for current, and it interacts in a magnetic field. Okay, and thus the discovery of the electron. Okay, so he hypothesized, okay, J.J. Thomson hypothesized that atoms are positively charged masses, okay, or spheres embedded with negatively charged particles called electrons. And he called his model his plum pudding or raisin bun model. Okay, it looks like a cookie. So a positively charged sphere with negatively charged particle. Okay, another representation of that is here, the pink sphere. Okay, next, there have also been some developments. So after the plum pudding model, the idea of a nuclear model emerged, and we have Ernest Rutherford to thank for it. Okay, so Ernest Rutherford proposed the nuclear model of the atom, and what does that mean? Okay, it just says that there is a positively charged body which he called nucleus, okay, and it is surrounded by the atoms which are at relatively large distances away from the nucleus, surrounded by electrons rather, which are very far from the nucleus. So what happens here is, or how did he come up with that idea, is through the thin gold foil experiment. Now this is the one that is very similar to your virtual lab on atomic models. So there is an alpha particle emitter, okay, but just like the similarity is in the virtual lab, you used light, white light. Okay, but nonetheless, that they are made up of particle-like substances. So for the virtual lab, you use photons. As for this, you use an alpha particle. So an alpha particle is basically a helium atom stripped of its electrons. So they bombarded a thin gold foil, and then he noticed that there are very few who bounced back, who got deflected, and most of them went through. Okay, and there are implications for the results of this experiment. And what are those? Well, number one is that an atom is mostly empty space. Okay, we are made up of atoms. That means we are also made up of mostly empty space. And there is a positively charged body which repelled the positively charged alpha particles. So that's the reason why the alpha particles bounce back. Okay, so 1 in a million chances it hit the nucleus and it got deflected. Okay, and I hope you've noticed this in the virtual experiments also. Okay, so he noticed that majority of the alpha rays just passed through while very few bounced back or were deflected. So that means there must be a body, a single body in an atom that is positively charged, which made the alpha particle bounce back. And he called that the nucleus, thus the nuclear model of the atom. Okay, so here are the implications. Gold atoms in the foil must be mostly empty space because of the alpha particles just went through the foil. Okay, because most of the alpha particles just went through the foil. An atom has a positive central core called nucleus, where the mass of the atom is concentrated. It is very dense, okay? And electrons are so tiny and spread out at such great distances around the nucleus. Now came also the planetary model of an atom. Now there are different versions of this. The first one is the Bohr planetary model, and it was later on developed into the Summerfield model. It's just a matter of the arrangement of the orbits. So once what happens here is he thought of the pathway of the electron as circular orbits around the nucleus, just like he thought of electrons revolving around the nucleus just like planets are revolving around the sun. So he said that what happens here is once an electron is hit by a photon, it receives energy from that photon and it moves a higher energy level or a higher orbit. Okay, but it cannot stay there forever. It always goes back down, and so it has to release that energy. So this is the principle behind the experiment. Uh, what happens? Why are there some registered colors even though you were using ultraviolet light? Okay, why are there very few registered red photons or blue photons even though you were using violet light, ultraviolet light? Okay, so in here, the farther the orbit is, or we call these energy levels, the farther the energy level is away from the nucleus, the higher the energy. So meaning it must take very large amount of energy for an electron to jump from the ground state, okay, this is the ground state, n is equal to 1, to a higher energy level, and it releases that energy. So this is depicted by the green spheres. Okay, photon is emitted with energy. Okay, and you know that energy is related to the photon's wavelength also, but more on that later on. Okay, and so the quantum mechanical or electron cloud model developed, and the main idea here is we cannot really determine the exact location of the electrons and its speed or its momentum simultaneously, meaning the location of an electron is uncertain and we can only guess so much of the probability. So he came up with the idea of orbitals, which are regions of space where electrons are most probably found. Okay, it is like the likelihood of finding an electron there. Okay, and we have these different types of orbitals, and I hope that you have mastered these, the SPDF, in your junior high. Okay, you also talked about quantum numbers. So these are the some pictures of those orbitals. So this is, for example, S, and then this P. Okay, the D looks like a clover leaf, and then it gets more complicated as we move to the F. All right. So that's it. That is how the atomic model, the concept of an atom, developed through the years, through so many years, and we are still working on it to have a more accurate, more refined, more scientifically proven model. And why is this important and why is this relevant? Okay, we know very well that atoms make up matter, and an understanding of the things that actually make up matter is very important for us to know its properties later on. Its properties, its uses, its benefits, and its harm. Okay? So thank you very much for listening, and I hope you enjoy the rest of the day.